Legged robots have great potential in navigating challenging terrains. However, to successfully handle terrains like slippery surfaces, it needs to identify the physical terrain properties of the footholds, or even anticipate it from vision before contact, so that it can choose a proper policy. In this work, we propose a multimodal self-supervised learning framework to pave the way for future training of physical terrain properties over locomotion and navigation policy. The first part of the framework is the physical decoders, which are neural networks and take as input the proprioceptive and height scan information and predicts terrain stiffness and friction per foot. We trained this module entirely in simulation. The second part is a vision pipeline, featurizing input RGB camera images and producing dense prediction of the physical parameters in the environment, and with a confidence mask to reason about the reliability of the output. The visual MLP network is trained online during real-world deployment with the labels provided by the physical decoders. In the first part, to train these decoders, we collect data set in parallel simulation by randomizing the friction and stiffness parameters per terrain patch. After training, we first validate the decoders in the simulation where the ground truth terrain physical parameters are available. Then we performed the real-world tests, and in the friction decoder part, compared our decoder with a friction-only baseline model from a previous work. Our physical decoders can not only sense the change of terrain physical parameters from interaction in time, but also correctly identify the difference between feet. To estimate the prediction error in real world, we use a digital twin experiment to compare whether the real-world prediction will result in a similar motion when rolling out the same action in simulation. By assigning each instance a different terrain friction value uniformly from range 0 to 1, we can identify the friction range with the lowest motion error. This range can be then used as the estimated friction parameter range of the real world. Here are two examples showcasing the different resulting motions. We then test the online vision pipeline in a controlled lab setting. The robot will walk across the whiteboard for 2 rounds. In round 1, there is little water on the whiteboard. When it transitions from the high friction ground to the whiteboard area, only limited slips occur. So the predicted friction value of the whiteboard does not differ much from the ground. When moving forward, footholds from the whiteboard to the ground will be projected to the camera image domain one after another. The confidence mask region changes accordingly. In round 2, we pour a lot of water on the whiteboard, making it very slippery. After the large slips occur, our visual network adapts to the new situation and predicts the large friction difference between ground and whiteboard correctly. We also evaluate the vision pipeline in 2 wild scenarios. The first one is the hiking test. Here we project the predicted friction image into the elevation map. The second one is the robots walking on grounds covered by heavy snow. Here we test the performance of the stiffness part. When the robot walks from the outdoor, soft, and snowy area to the indoor rigid ground, the stiffness prediction also rises significantly, and our model gives a reasonable confidence mask in both experiments.